Math 2414, Representing Functions as Power Series, Video 1, reviewing a very useful series. When we first looked at geometric series a few sections ago, I had done one video about something called a very useful series. But before we get to that, let's quickly review what it means for a series to be geometric and under which conditions it converges and what it converges to. And let's correct the typo. There we go. We call it a geometric series whose first term is A. Let's underline that or circle it because it's kind of just sitting there. And whose ratio is R. We did require the absolute value of R to be less than 1 to get convergence. Actually, we didn't require it. That was just a characteristic. One second, folks. That was just a characteristic of being a geometric series. There we go. Position on my video, so when I look at my camera, I'm actually looking at you. Excuse me, when I look at me, I'm looking at you, because if I put it off to the side, I'm like, Anyway, but recall that for a geometric series whose first term is A and whose ratio is R, absolute value of R less than 1, then this series converges as follows. Remember that what makes this series geometric is that you multiply times the same constant to get from one term to the next. In this case, we're multiplying by R to move from one term to the next. And if you have a geometric series that starts with A with a common ratio of R, then we can write it two different ways. Number one is as a sum. We could write this as n equals 0 to infinity of A times R to the n. That's pretty easy to see because each term has an A in front and each term has a power of R, but the powers of R start at 0 since anything to the 0 power is 1. Well, except 0 to the 0 power, but let's not hash that out right now. But if we have our if we have our ratio small enough, then the geometric series will always converge to the first term over 1 minus the ratio. In this case, the first term being A and the ratio being R. I still do prefer saying first term over 1 minus the ratio. But now what we're going to do is we're going to reverse engineer not from series to function, but from function to series, meaning that we need to be able to identify what piece of it is the first term, which piece of it is the ratio, and be able to restore it back into a sum. So in previous videos, when I said I'm not really worried about the structure of the sum when you're writing a geometric series, I'm going to have to change course on that and say that if you know the first term in the ratio, this is how you can set up the sum. Start at 0, go to infinity, first term, ratio to the nth power, because we're going to be doing quite a bit of that. But that wasn't the very useful series. The very useful series was we could define a function, f of x, as follows over the interval -1 to 1. F of x equals 1 over 1 minus x, which is a pretty innocuous function in its own right. But if we look at it from the perspective of a geometric series, then this 1 would be the first term. So that's our A, if you will. And this x would be the ratio, so R. And as a consequence, we can build this geometric series, this power series, to represent that function. Let's get rid of all the red stuff and blue stuff. Because if we were to look at this as a geometric series, or the sum of a geometric series, the first term would be 1 and the ratio would be x. So we would just multiply by x over and over to get the next terms, which should be pretty clear that that's just the sum of x to the n as n goes from 0 to infinity, plus ... excuse me. And again, we get convergence if the absolute value of the ratio is less than 1, which is the same as saying -1 is less than x is less than 1. We do get divergence at the endpoints. Not always the case. when you have an interval of convergence, but for a geometric series, it's always the case. So what does this even mean? What does this look like visually? I mean, if you go back to college algebra, this is a pretty standard graphing problem. There's a vertical asymptote at x equals 1. The horizontal asymptote is y equals 0. We could graph it and do other stuff with it. But how can you compare a graph of something from there with a graph of something that has an infinite number of terms? Well, the answer is we look at some partial sums. For example, if we take the nth partial sum, that means we would just stop the sum at some number n. We could say the kth partial sum, since n is already being used as the index in the sum. Let's say the kth partial sum. And that's just a finite polynomial. So it's got a polynomial graph that does its curvy stuff. But what do the graphs of these partial sums look like compared to the graph of 1 over 1 minus x? Well, let's jump into Desmos and take a look at it real quick. In Desmos, I got a few things set up. The first of which is just the graph of f of x equals 1 over x, which does precisely what we thought it would do. It has a vertical asymptote at x equals 1. It has a horizontal asymptote at y equals 0. I guess I could graph both of those, or not. How about this? Can't stop me. Maybe it can. All right, but anyway, so it's got a vertical asymptote, a horizontal asymptote at y equals 0, and a vertical asymptote at x equals 1. But what about this series? If you'll notice, I've got a sum set up here that is ready to add up powers of x, going from 0 to k. Now, right now, k is set at 0, but I can move it so that the number of powers it adds is greater. For example, there's when k equals 1. So this would be x to the 0 plus x to the first, or 1 plus x, or x plus 1. Y equals x plus 1. So it's just that line. But as I move the slider up and increase the upper limit on the sum, now I get a parabola, which makes sense because if you think about it, this upper limit is the power we stop at. So we get a parabola. But as I raise the index, I start getting curvier and curvier graphs. In fact, I can animate this so that it will just start raising the powers for me. Right now, it's having a 12 as an upper limit. So it's going from the 0th power of x to the 12th power of x, 1 plus x squared plus x cubed plus x to the 4th, all the way to x to the 12th. And as I animate this and let it keep raising the upper limit, it does slow down when it's graphing because it's got to do a lot of calculations. But right now, I'm at a 30th degree polynomial, adding all the way from 1 plus x squared all the way to x to the 30th. And if you notice, I've got this little knife-looking shape. If I slide this all the way over to 100, it's calculating. It's not done, I can tell. I can tell because for an even degree polynomial with the positive leading coefficient, both ends are supposed to point up. But now it's done, and it really looks like a knife. But how does this compare to our original function? Well, if you notice, it kind of overlaps it. Not completely, looks completely overlapped there, but it's not even touching over there. So why does it match almost perfectly? It's a big polynomial. It takes a while to turn on and off. We'll turn the red one on and off. Why does it match almost perfectly just on that portion, but not to the left over here, and certainly not on the right over there? Well, the answer is the interval of convergence. I'm going to bring up a couple of vertical lines at x equals -1 and x equals +1, which was our interval of convergence for the very useful power series. And notice that the blue graph and the red graph are practically identical by the time we've reached x to the 100th power. Let's take it back down a few notches, like back down to the 8th power for a second. And notice that if we were to zoom in, you would see that, yeah, they're kind of the same, but they start to split here. Let's zoom in a little bit more right here. So they start diverging from each other. And if we go to the other end, they look like they're sitting on top of each other, but as we get further and further away from the center, you'll notice that they are starting to diverge from each other. So yeah, this is doing everything we expected it to do. We expected this partial sum, if you will, to pretty much be this original function. We expected this partial sum to pretty much match that, at least between -1 and 1. But you know, the larger we make the partial sum, the closer we get to matching the graph, but only over its interval of convergence. I'm going to take it all the way back up to 100, give it a second to think. I don't think it's quite done yet. There we go. It made a move. But even when we went out to x to the 100th, if you were to get really close to x equals -1 here, you'll notice that, yeah, it's really close, but then it splits off. If I wanted to get a closer approximation over here, I would need to raise the power up a whole lot. So it's thinking because of the 100th degree polynomial. Every time I zoom in or out, it's got to recalculate a bunch of stuff. But my point is, our power series, whose graph is represented in blue, at least up to 100 for the upper limit, looks just like my graph, but only between -1 and 1. So what are we going to do with this? Let's go back to the whiteboard for a second. What are we going to do with this? Well, what we're going to do is we're going to use this series to represent many other functions as power series, using some tricks that you may or may not think of in advance, but once we see them, they're actually pretty straightforward. You just have to stay focused and you're gonna be okay.